Well, good morning, everybody. Welcome back to the department's colloquium. And as you know, the theme for this quarter is integrated systems and circuits. And so we've had a collection of speakers from various areas and people doing research on chips and new devices and architecture. And that will be the theme for the rest of the quarter. Today's presentation, I'll just kind of give a very high level view of it. This will be a presentation that's related to analog, really kind of hardcore analog circuit design. And specifically, if we look at the big picture, as I mentioned perhaps at the beginning of the quarter, and as my students in my class know, that one particular area of analog circuit design that's of a great interest from a research perspective is the implementation of high performance analog circuits in basically CMOS technologies, right? Where the technology and the transistor is really flavored for digital applications, but we would like to realize high performance analog circuits, even though the transistor really isn't favorable for that particular application. And this is a good example of that right here. So audio amplifiers traditionally have been confined to, using actually vacuum tube transistors, right? You can get a high voltage across them, and they're very linear. You can get them to be very low noise, and so a very high dynamic range. So researchers like Qinwen, what they're looking at doing is, again, trying to get that kind of performance out of really using a technology that's not meant for this application, being CMOS. And of course, the big advantage is you can get the audio amplifier portion on the chip, then you can combine it with all the digital signal processing. You can play all sorts of new system tricks, and it kind of opens the door to a whole new area. So without further ado, I'd like to introduce our guest speaker from Delft University. So we're really excited about having her here today. And so Dr. Qinwen Fan, she received a BS degree in electronic science and technology from Nankai University in China. And then she continued on at Delft University. From 2012 to 2015, she worked at Maxim Integrated Products in Delft, which was a company doing satellite, actually, chipsets for and set-top boxes. And then she transitioned to Melinex, also in Delft. And then in 2017, she joined Delft University as an assistant professor. Her current research interests are in precision analog, Class D amplifiers, DC to DC converters for energy harvesting, and current sensing amplifiers. Dr. Fan is an associate editor for the Open Journal of the Solid State Circuit Society. And she's also a TPC member for the International Solid State Circuits Conference and the European Solid State Circuits Conference. So without further ado, I would like Dr. Fan to take it away.
Yeah, thank you. Thank you very much for the introduction. And it's really my honor to talk here today. And I learned that maybe most of you are not so familiar with Class D audio amplifiers. And I hope that after this talk, you will find this topic a bit interesting. Let's get started. So in this talk, I'm going to cover several topics. First, I would like to say something about Class D audio amplifiers in a nutshell. So how does the basic system look like? And why do we use Class D, not Class A, B, C, D? What does D mean? And then also something about the modulation scheme. What does that do? And then also something about the Class D output stage configuration and some topologies. And after that, I would like to point out what are the benefits of a high switching frequency Class D amplifier. And this is something we have done some work in the past 3-4 years. And then in the end, I would like to give some design examples with high switching frequencies. So here we have 3 different topologies. The first one, we're using a delta sigma modulation and PWM modulation in a hybrid form. And then in the second one, we have a pure PWM modulation Class D amplifier with low EMI. And the last one, we are tackling the linearity issues in the LC filter, which you often find in the audio system as well. And in the end, I will give a summary and conclusion. So to begin with, we have a lot of applications for audio amplifiers, as you all know, that in virtual realities, automobiles, home theaters, and headsets, cell phones, even personal health, such as hearing aids, you need audio amplifiers. And if we talk about audio signal, then we're talking about signals from 20 hertz to about 20 kilohertz. And then if we talk about the power of these amplifiers, they can range between tens of milliwatts, that's usually like in a hearing aid, and then to even thousands of watts. And that is when you're looking at these really huge theater speakers, or even some fancy high-end home theater systems. And even in some of the modern cars, you can also find a 1,000-watt speaker driver. So how does this system look like? Well, it looks pretty simple in the basic form. First of all, you have this source, and that can be both in the analog form or digital form. Of course, nowadays, digital is getting more and more dominating. And then we have the audio amplifier, and this amplifier really needs to get the signal, process the audio signals, and then pump a lot of power into a speaker. And over here, we see a dynamic speaker. This is still the most dominating speaker on the market. So basically, if you model it in an electrical fashion, then you can model it into two parts. You can model this in the electrical part, which is the most interesting for us electrical engineers. And you can simply model it as a resistor and an inductor. So sometimes maybe if you look at some data sheet or read some paper, people will say this is a 4 ohm speaker or 8 ohm speaker. Then that 4 ohm or 8 ohm is referring to this resistor. But the total electrical part of the speaker basically consists of not only the resistor, but also this inductor over here. And then, of course, there's also the mechanical part about how you produce the sound. You have to have a chamber and so, and there you can also make a model with RCL. But this part is a little bit more about the physical design of this speaker. It's not so much related to the electronic design. And so if we look at the audio amplifiers, we actually have many different choices. And here you have all kinds of different classes. So all these different classes, they refer to different amplifier topologies. And so class A amplifier, for instance, refers to an output stage where you have a biasing current source and then an output transistor. And then class AB is a little bit more advanced compared to that in the sense that it doesn't require a biasing current source anymore. It can pump more output current. And then we have class H and class G, and these two classes of amplifiers, they are trying to adapt the supply rails according to the signals to improve the efficiency. And in the end, we have the class D amplifier. So what does this amplifier look like? Well, the class D amplifier in the simplest form, you can think about it just as a inverter or consisting of two switches. And this load, you can imagine this as the speaker. Now I'm not drawing the inductor. I'm doing this in the simplest form. So imagine this is just a speaker. And all you are doing is basically switching the speaker between two supply rails. And of course, these two switches are not opening or closing at the same time. They are driven in an inverter fashion. And you also want to make sure that there is not a moment that both of these switches are switched on, because otherwise you're creating a short circuit. So by doing this, you're basically doing a switching amplifier operation, and at output, you are producing this kind of a square wave, sort of like waveforms. And you might wonder, yeah, how does this produce sound, right? I will talk about that a little bit later, because you need to get a modulation scheme to make sure that this waveform actually represents the sound content. But if we just look at this output stage and think about power efficiency, this is actually the best you can do with CMOS technology. Now, this is because when you're pumping a lot of current to the load, and this current is only flowing through either one switch or the other. Now, in CMOS technology, you can make these switches very large, and then you can make their on resistance very, very small. Now, this is really the closest thing that you can get when you want to improve the power efficiency. You just want to make these switch on resistance as low as possible. So then the power loss in these switches is basically I squared R, and that is as low as possible. So this type of Class D amplifier is much more efficient compared to all the other more like analog type of amplifiers. And if you're still not convinced, then if we look at this graph, now you can see that with all different types of amplifiers, Class D amplifier really tops them out. So for instance, this is a Class A amplifier where you have a current source and output transistor, and then you have the Class AB and Class G and H. They are just not comparable to Class D amplifier. So the next question is, okay, now I can produce these switching waveforms, and I can design these switches to have very low on resistance to reduce the power loss in this stage. The question now is, how do I make this waveform representing audio content? Now, to do that, you need to have some kind of modulation scheme. So typically we use two types of modulation scheme, and one is called DSM, delta sigma modulator or pulse density modulator, and then you can also use a PWM modulation. And in a lot of the audio amplifiers, we see PWM is being a little bit more dominating compared to a DSM, but DSM is also perfectly fine in doing the modulation job. So how does a PWM work? Well, PWM is quite simple, actually. So imagine this signal, this green one is just your audio signal in the analog form. What you're basically doing is that you are comparing this analog signal to a triangle carrier. So this carrier normally has a much higher frequency compared to the analog signal. And you just use a comparator to compare the two. And then you will produce a output waveform. This is two-level, more like square wave or type of waveform. And this waveform, you can use this to directly drive the Class D amplifier output stage. Now, without going into a lot of math into this, but if you just look at the frequency spectrum of this PWM modulation, you will see that it actually produces this kind of frequency spectrum. So at audio band, we still have the audio signal. This is this red one. And then, of course, with all these switching waveforms, you expect quite some high frequency content. And this is also true if you look at the frequency domain. So in fact, at the PWM frequency and its multiples, you will see a lot of harmonics. But this ideally may not be an issue because in the end, our speaker is only going to make sound in the audio band, and our human ears can only hear the signals in this audio band. Now, another type of modulation is the pulse density modulation. That is what you do when you have a delta sigma modulator. And what this one is doing is you have the analog signal at the input, and then you have a quantizer. In this case, is a 1-bit quantizer. You're trying to basically tell the sign of the signal, whether it's positive or negative. And then you have a 1-bit signal. Then you can drive the Class D output stage, and then you feed back the signal to the input. Because this is a feedback system, so the output is going to contain the audio content at the audio frequency, assuming that this feedback loop has a lot of gain in the audio band, which is usually the case because audio band is at quite low frequency. It's quite possible to achieve good gain. Now, of course, we have all these high frequency content. This is the quantization noise from this sigma delta modulator. And so if you look at the frequency spectrum, you see quite a lot of quantization noise that is going up to actually half of the switching frequency of this system. But luckily, if we just look at the audio band, it is still relatively clean as long as we can push all of this noise out of band. And so this is about the modulation. And what about the output stage configurations? Well, nowadays, you will find almost everywhere the so-called bridge tied load configuration. So this is a differential output stage configuration. So you have one inverter output stage, and then you have another one. And then you just tie your speaker between these two stages. And there are many different ways to drive this output stage. So for instance, one of the ways to drive it is called the AD mode. And this is the fully differential mode. What does it mean? It means that whatever signal that is driving the left half of this bridge, you use the complementary signal to drive the right half of the bridge. So this whole output stage is basically a fully differential complementary stage. And so if you look at the differential signal that is applied on the speaker, then you will see that it's basically identical to one of the drive signals. And if you look at the common mode content, it is ideally 0 because these two signals are complementary. Now, there is also another way to drive this output stage, this BTL output stage, and that is called the BD modulation. And how does this work? So in this case, you produce the complementary analog audio signal like this, and then you compare this with the same triangular carrier. So with these two comparisons, you can generate two different types of 1-bit signal. And then you use these two signals to drive the two halves of the H bridge. Now, the nice thing about this is that if you look at the differential output applied on the speaker, you see you have a 3-level signal. And the nice thing about this is if you look at the switching frequency, is effectively twice of the carrier frequency. Now, why is that beneficial? Later on, I will show that having a higher effective switching frequency is actually quite beneficial for the Class D amplifier to achieve a better linearity. So this is something we will talk about a little bit later. Now, the drawback, of course, in this stage is that because the left half and right half are not completely complementary, now it has a common mode content. And the common mode content can be an issue in some of the applications because it can cause some common mode EMI problem. Now, why is that an issue? You can imagine because this is differential configuration, you normally have two cables. Now, when you have two cables running together, you can twist them or put them very close. And then if you think about the magnetic interference generated on both these cables, if they are fully differential, then they sort of cancel out. But if you have a common mode EMI, electromagnetic interference, then they cannot cancel out, and then that could be a big problem. So these are the advantages and disadvantage of the two different modulation mode. And then we also can take a look at the Class D amplifier topologies. So the first topology is basically just an open loop topology. And in this case, you can actually imagine that the loop filter is just a amplifier, just like a block with gain of 1. And then you just feed a signal to the modulator, and the modulator can produce this 1-bit signal that drives the output stage. So you can either produce AD mode or BD mode, and then that's it. The Class D output stage would just drive the speaker. Now, the problem of this is that you can imagine the Class D output stage produces a signal that is switching between the power supply, right? So if you have some variations on the power supply, let's say this V supply is not constant, it changes for somehow, or if there is some interference, then this interference and error would directly translate into error in the output signal. And therefore, it will degrade the audio signal quality. So to solve this issue, what people normally do is to have a closed loop configuration. And what does this do? Well, the feedback basically takes the output signal and compare it to the input signal. And when you have a lot of loop gain, so in this case, the loop filter needs to have a certain gain. When it has a sufficient gain in the audio band, then the output audio signal will be a faithful copy of the input audio signal, regardless of supply variations. So this is why in a lot of high-end audio products, you will see probably closed loop amplifiers. And then we also have the digital input and analog input. So many, let's say, conventional Class D amplifiers still have the analog input. But nowadays, of course, we see more and more digital input Class D amplifier, simply because with digital, there's a lot of flexibilities. You can do a lot of nice things. You can implement pre-distortion in the digital format. So digital input is becoming more and more dominant in the industry. Now, of course, with digital input, you have to do something with the entire topology. But first of all, if you still want to use this analog loop, you need to have a DAC, that is digital to analog converter at the input. So by doing this, you basically translate the digital signals into analog signal, and then you can use a good old analog loop. And another way to do this is you basically change the analog loop also into a digital loop. And so you have digital loop filter instead of analog loop filter, and then you have digital modulator, and then you're using this to drive the H bridge. But because in the end, at output of the H bridge, it is still producing an analog signal. So you have to have an analog to digital converter in this entire system. So in the feedback, we have an ADC, an analog to digital converter needed. And now a lot of the burdens of the system is basically on this ADC, because the ADC now needs to faithfully convert the audio signal at the output of the H bridge to a digital representation. And then if the loop has a lot of gain, then this output analog audio signal will be a faithful representation of the digital input. So these are some of the topologies we can find in Class D audio amplifiers. And now let's talk about some other important things in audio systems. And this has something to do with EMI, so electromagnetic interference. What does that mean? Well, when you have an amplifier like Class D audio amplifiers, it will produce a lot of high frequency noises, right? And often, if the speaker is far away from the amplifier, well, far away, I'm talking about something larger than 10 centimeters, for instance, then with this cable, there will be a lot of electromagnetic interference emitted. Now, if you have other electronics, let's say in a car, for instance, they can be very sensitive to this kind of noise. So in cars, for instance, we have very strict EMI rules to make sure that everything that you put, every electronics that you put in a part in the car needs to fulfill this standard so that it doesn't disturb the other electronics. Now, it's also the same for the Class D audio amplifiers if you want to put it in a car. And so to solve this problem, you might say, okay, let's just put the Class D amplifier with and the speaker very close, right? But it is often not the case, because in a car, it can be a very sophisticated environment, and it's not just up to us, the audio amplifier designers, to decide what can be put close to what. So often the physical limitations would imply that there will be a distance, so you have to use these cables. But then how do you restrict these EMI? Now, what people normally do in this case is that they have an LC filter after the Class D audio amplifiers immediately. And these LC filter will filter out all these high frequency content, and then you connect the cable to this LC filter output to the speaker. Now, over here, it is mostly just audio signal, so we don't worry about EMI anymore. Now, some of you may wonder, why do you use LC filter, not RC filter? Well, this is because, again, about the power efficiency, because just think about that you want to pump 1,000 watt into the speaker, you need to pump a lot of current into this speaker. So the use of any resistive element would be very, very difficult if you want to maintain a good power efficiency. So LC filter is almost the only choice that you can put over here. Now, of course, when you put such a thing in your system, then you are increasing the cost. Because nowadays, most of the LC filters audio systems are using, they are still external components. They are still relatively big. So if you look at the cost of the entire system, this LC filter can easily be a large percentage of the entire system. And moreover, these LC filters can introduce nonlinearity. Well, that is because the L and the C, these values could change according to the signal content. So you will find out that, okay, you put a lot of effort in making a very nice Class D amplifier, but maybe because you're not careful, you have not selected a very linear LC filter. Now, in the end, the entire system nonlinearity is just bottlenecked by this LC filter. So later on, I will also show you how we can tackle that issue. So to tackle this issue, actually, from the system level, the simplest thing to do is just to move the feedback from the input of the LC filter to the output of the LC filter. Now, the action of a feedback loop is simply that you take the signal at the output point, and then you compare it to the input. And assuming if your loop is stable and has a lot of gain, then the output signal will be a faithful copy of the input. So by putting the LC filter inside this feedback loop, we are also correcting the LC filter's nonlinearity. Now, of course, if you're familiar with this LC filter frequency response, you know, okay, this is 2 poles, and that is not very easy to stabilize, especially if you look at the loop. It has a loop filter, probably it has more poles. So how do you stabilize this system? That is a little bit challenging. So later on, I will show a design example how we actually tackle this issue. So to summarize, if we look at the conventional Class D amplifier systems and assume that you need an LC filter because of you need a long, relatively long cable, then there are several things that you want to consider. The first thing is you want to consider the nonlinearity of this Class D output stage. Now, I haven't talked about this too much, but just imagine this switch, this output stage is basically 4 switches. Now, how do you switch on and off these switches? You need to be very careful. You cannot switch them on at the same time because you are going to create a short circuit between the supplies. So you need to be a little bit conservative to make sure that not all of them are on at the same time. So we're doing this by having a little bit of the dead band, meaning that the dead time, meaning that at a very brief moment, all these switches are actually off, especially when you're transitioning from closing this switch to closing the switch on the top. So when you're doing this kind of measures, you're introducing a state where all of these switches are off. And that does not actually represent the ideal PWM waveforms you want to produce. which means you will introduce some nonlinearity in this output stage. Now, the higher the power you want to pump to the speaker, the bigger these switches will become, the slower they will switch, and the longer the dead time will be. So in other words, the more nonlinear it will be. So this is the nonlinearity that you have to consider. And then another nonlinearity is what I mentioned earlier, is when you use these external LC filters, you have to be very careful because they are not that linear. If you look at the data sheet, the L and C values would change with the signals. And at the same time, these LC filters can be also very costly and bulky. So when you're designing such audio systems, you need to consider at least these different aspects. And if we look at the, let's say the conventional Class D audio amplifiers, they mostly employ PWM modulation, and they are switching around 150 kilohertz to about 500 kilohertz. Now, what is the problem in that? Well, first of all, this frequency is relatively low, and which means that you will have quite some harmonics at these carriers and their multiples. Now, the bad news is that the AM band is actually right covering these zones. So to make sure that you don't emit any EMI signals into the AM band, then you have to use a relatively large LC filter to filter out all these PWM frequency tones. So this means that your LC filter cutoff frequency has to be relatively low, usually around 40 kilohertz. And another limitation this will bring is that because of the switching frequency is quite low, it also limits the loop gain. Now, how do you understand this intuitively? Well, you can imagine that the loop have to process a lot of these high frequency components. Now, if you are feeding all these high frequency components to this PWM modulator, that could create a lot of intermodulation problems, because this PWM modulator, ideally, it wants to compare an analog signal with the carriers. Now, instead of having just an analog signal, you're also having a lot of high frequency component in it, and that will confuse the PWM modulator. So you want to have a loop filter before it to filter out all those high frequency components. And that means the loop filter needs to have a lower cutoff frequency to filter them out. So the lower the switching frequency, then the lower the cutoff frequency, the bandwidth of this loop filter would be. So the slower the entire system will be. And this also in analog domain also means that if you have a lower bandwidth of the system, it is also more difficult to achieve a higher loop gain. And if you have a lower loop gain, then you do not have a lot of capability to correct the nonlinearity of the output stage. So overall, it is quite an issue in a conventional Class D audio amplifier. And then we also talked about if we want to correct the nonlinearity of the LC filter, ideally you want to bring the feedback after the LC filter. But in this case, it is complicated because the LC filter introduces two poles. So you need to introduce some zeros to correct the phase margin to stabilize the loop. But now if the loop entirely has a relatively low bandwidth, then there is very little wiggle room for you to play around with these zeros and poles and to make sure that you get sufficient phase margin. So to overcome these issues, actually a very simple way to solve these is to increase the switching frequency. Now, if you increase the switching frequency, it means that the loop filter bandwidth can be increased because you don't have to filter out a lot of these relatively low frequency PWM harmonics. Then you have a better chance to realize a higher loop gain in this loop filter. And therefore you can offer better linearity. And then also because the switching frequency is higher, the LC filter doesn't have to work so hard to filter out all these harmonics. So you can relax the LC filter cutoff frequency. Now, if you relax the cutoff frequency, you can use smaller components, so they can be hopefully smaller and cheaper. And then also, because the switching frequency is higher, the loop bandwidth is higher, so you have a more wiggle room to play around with placing extra zeros to compensate the phase delay introduced by the LC filter. So overall, we will show that it's quite possible to bring the feedback after the LC and still achieve a very good stability in the entire system. And lastly, also very interestingly, we see that actually increasing the switching frequency would ease the EMI management in some of the applications. Now, I will talk about that in the next couple of slides. So first, let me just elaborate a little bit more about loop gain and switching frequency in case you are not very familiar with the Class D amplifier system. So again, when we have this feedback structure of a Class D amplifier, then we rely on this analog loop filter to produce a lot of loop gain. Now, always remember, the higher the loop gain, the better the output signal will copy the input signal. So you always want to have a lot of loop gain. Now, in an analog system, usually we have a loop filter and we implement a certain order, right? So if you look at, if you just plot the loop gain of the entire system over frequency, you will see that, for instance, this is one of the loop gain that with a loop bandwidth that is around 100 kilohertz. Now, imagine that for the same order of loop filter, I now increase the loop bandwidth to higher, let's say 500 kilohertz. Then basically you can immediately push this loop gain to the right-hand side. And that means you are gaining quite a lot of loop gain at the same frequencies. And if you look at the audio band that is from 20 hertz to here is 20 kilohertz, you see that simply by pushing the unit gain frequency, the bandwidth of the loop filter to a higher frequency, you can gain quite a lot of loop gain over here. So that means you have more capability to correct the nonlinearities in the Class D output stage. Another thing is about EMI. And that is when we think about applications like automotive, for instance, you have this CISPR 25 Class E regulations that you want to comply. And this regulation means that you cannot emit energy, or you cannot emit high energy in particular band. So if you look at the shaded bandwidth, there are the bandwidths that you cannot emit a lot of energy. And so if you switch the Class D amplifiers in like the traditional way, which is about 300 kilohertz to 500 kilohertz, that would be this red arrow over here. So you can place this in the gap. However, remember that PWM also has energies around its multiples. So you can avoid this first EMI, you can avoid these two EMI masks with the first harmonic, but with the second harmonic and third and so on, you are not so lucky anymore. So to make sure that these harmonics also do not penetrate through the EMI mask, you need to have a LC filter that is sufficient to filter out all these energies. And that is why traditionally people have to use 20 to 40 kilohertz LC cutoff frequency. Now, interestingly, if you look at the scenario where you switch at a higher frequency, in this case, just a little bit beyond 2 megahertz, then you see that you can avoid all these difficult EMI masks. And even there is quite a big gap over here. Now, everything is plotted in log, so it looks, well, it's not a big gap, but actually in the frequency domain is quite a big gap. So a lot of these harmonics will also be placed in this gap. And that means you can greatly relax the filtering task of this LC filter. So if you look at the first product, that was doing this, that was from TI, and they have realized an LC cutoff frequency at 88 kilohertz, and that is already 2 to 4 improvement over the conventional solutions. So, but you might wonder, what are the disadvantages of switching at higher frequency? It cannot be all good, right? And that's correct. There is always a catch in analog circuit design. And one of the problems is that if we are switching at a higher frequency, you need to be careful about whether your output stage can do. Now, because, okay, 2 megahertz maybe is not so difficult in the digital domain nowadays, and you can produce really sharp digital waveforms with 2 megahertz, no problem. But keep in mind that the Class D amplifier has a very big output stage to pump amps of current into the speaker. Now, that output stage may not be able to have the slew rate, the switching speed that is really catching up to 2 megahertz. So what will happen in the reality is that the output stage of a Class D amplifier will not have these sharp edges, but it more switches like this. So you have this transition moment. And so instead of producing a very faithful 2-level, let's say a square wave PWM signal, it will produce something like this. Now this will translate into distortion. So one way, of course, is to increase the loop gain to correct this, but then we were also looking at other alternatives. Is there any way we can sort of mitigate this in some other ways? Now, one solution that could pop up is to use a 1-bit delta sigma modulator. Now, how does that work? Well, with the delta sigma modulator, the nice thing is that the pulse will always be equal or larger than the sampling rate of the data converter. Now, if you think about the PWM case, where you compare an analog signal with a triangle wave, if the signal goes really big, let's say if the signal is approaching, for instance, in this case, if the signal is very big and is approaching the tip of your triangle carrier, then this pulse can be theoretically approaching 0, right? So that is what happens in PWM, and that can be extremely difficult for the Class D output stage to produce. However, in the delta sigma modulator, the pulse width is always limited by the sampling rate of the system. So that means you can define a minimum pulse width which can be handled by the output stage of the Class D audio amplifier. So then we thought about, let's just use the delta sigma modulator to make this Class D amplifier. Now, of course, this way, there are other problems. When you use a 1-bit delta sigma modulator, you have a well-defined pulse. You don't worry so much about output stage not being able to catch up. But at the same time, you're producing a lot of quantization noise. Now, if you look at this noise in the frequency domain, you see that this noise can again penetrate through these EMI masks. And therefore, again, you need a pretty large LC filter to filter them out. So this is not so nice. Now, is there any way that we can bring down this quantization noise level? Well, there is a way, and that is basically to use a multi-level quantization. Now, what does a multi-level quantization mean? It just means instead of having just a 1-bit quantizer, which is just a comparator, you can have a multiple comparators that has different threshold. So this multiple quantizer can have multiple levels at its output. So instead of having just, let's say, 0 and 1, this multi-bit quantizer can output many different levels. And if you take things to the extreme, if you have infinite number of levels in this multi-bit quantizer, you're basically producing an analog signal at its output. And when you're producing an analog signal at its output, there is no quantization noise added. So that is how you can think about this. The more levels you add, the less quantization noise you add to the system, and therefore, the more relaxed the LC filters will be. Now there comes a question, okay, if I have a multi-bit quantizer, now I need to have many different levels, right? So instead of having just the 0 and the supply, now I'm adding a lot of levels between these two supply rails. That is easy to do in with digital circuitries, with quantizers, but how can I produce these levels with Class D output stage? That is very difficult, because to do that, you need a lot of different supplies and a lot of different output stages. And that is not going to fly, because these stages has to pump amps of current to the speaker. So they are really huge. And you don't want to have a lot of them. You want to just have one of them, as few as possible. So we sort of realized, okay, you have to stick to this 1-bit output stage. But for the quantization noise reason, you want to have a lot of quantization. So we have now a mismatch, right? On one hand, we want to have a lot of quantization level, but on one hand, we have a 1-bit output stage. So what do we do in between? Well, it turns out that there is a good way of doing this, and that is to use a converter to convert this multi-bit signal into 1-bit. So how can we do that? Well, this is actually very simple. This is basically using the thermometer code that is coming out of this multi-bit quantizer. So let's say in this case, it's very simple. We have a 2-bit quantizer. And imagine we have these 3 different scenarios. We have 1, 1, 1, 0, and 0, 0. Now our task is to convert this signal into a 1-bit signal. So then over here, let's say when we have 1, 1, now we just create 2 different time slots. So over here we have 1 in this time slot. And then we have 1 also in the second time slot. And for the combination of 1, 0, what we do is that for the first time slot, we assign 1 to it. And then for the second time slot, we assign 0 to it. And then when you have 0, 0, then you assign 0 to both of the time slots. So in this way, by converting this signal into the time domain, we can actually convert a multi-bit quantizer output to a 1-bit output signal. So this is very handy, and this can work with our Class D audio amplifiers. And of course, you can make things even more sophisticated. You can have a lot of different levels, and then you can assign many different time slots into this conversion. But in the end, the idea is to convert a multi-level quantizer output into a 1-bit signal. So then in the end, this is what we do. And in some of the cases, we still would end up with very small pulse. Now, why is that so? Well, if you look at this conversion, right? So we have a lot of 1, 1, 1, 1, and we have, for instance, over here, when we have the signal level that is 0.9. So we have 1, 1, 1, 1, and then only 1, 0. So that means we have separated a lot of different time slots into this period. We assign most of them to 1, but then we assign only 1 to 0. Right? So there's only a very short amount of time that the output is 0. Now this would exhibit again as a very small pulse. And this could be very difficult to handle for the system again. So knowing what our output stage can handle, we want to maximize this. And what we did was that we adopted a non-uniform quantization. So that means with small signals, we're still doing the same kind of coding, but when the signal has increased to a certain level, we have chosen to reduce the number of levels so that the minimum pulse width in this case would stay at a certain number that our output stage can handle. Now you might ask, okay, now you are losing a lot of levels, some levels for large signal. Does that do a lot of damage to the system? Well, the answer is almost no, because the audio signal has a very high crest factor. What does that mean? That means that most of the time your audio amplifier is not outputting full scale signal. Most of the time is actually outputting relatively small signals, maybe 10 times smaller than the full scale. So most of the time we are in these fine conversion zone. Only a very small amount of times we are at these very large signal level, so that the linearity degradation of the entire system is not that significant by choosing this non-uniform level scheme. And also we have done single-sided, we have done a double-sided modulation instead of a single-sided modulation. Now, what does that mean? Okay, so if you look at this conversion, right, so here we have a lot of different quantizer output, and then we convert them into the 1-bit PWM signal. Now, if you just do this, let's say in this fashion, so you have a lot of 1 and then you assign 0 at the end of one cycle, this is the waveform you will end up with. Now, what we chose to do is that we flip the second cycle so that the zeros in the second cycle would come first. So then you come up with a waveform that is looking like this. Now, again, you might wonder, yeah, what does this bring? The good thing is that this one basically reduces the switching activities in the output stage by half. Now, that is also important because every time you are switching on and off these huge transistors, you have to pump in a lot of current to drive these transistors. And you don't want to do that very often because every time you do this, you are losing some power. So this will reduce the power efficiency of the system. And therefore, we have chosen to use a double-sided modulation to reduce the switching transitions. And so in the end, the system have achieved a pretty good estimated EMI performance. So for instance, the black one over here is showing, this one is showing the conventional 1-bit delta sigma modulation, and the green one is showing the multi-level PWM and delta sigma hybrid conversion. So with this modulation scheme and the number of levels, we were able to achieve a very high SQNR that is 120 dB. If you're not familiar with it, you may not know what it means, but this is a very good number for Class D audio amplifiers. And then just to give you a brief overview, you don't have to understand all the details of this. I'll just try to make this as intuitive as possible. So we have a third order loop filter. Well, to have a higher order of loop filter helps you to pump up the loop gain in the audio band. And then we are also adopting a 4 megahertz switching frequency. This is almost 10 times higher than the conventional switching frequency. So this helps a lot to increase the loop bandwidth and also to achieve a higher loop gain. And then we also have a 17-level non-uniform flash quantizer. So to have this multi-level quantizer, the main purpose is to reduce the quantization noise so that you don't need to use a large LC filter to filter them out to meet the EMI standard. And then, of course, we're using a multi-level quantizer to 1-bit PWM converter to make sure that we can still use the 1-bit traditional Class D output stage. So in the end, everything was implemented on chip in a TSMC BCD 180 nanometer process. So this is by no means a very advanced process for digital and so. But this is a very nice process for Class D audio amplifiers because it produces all these very nice LD mosses for the output stage. And if you look at some of the performance, we have measured the THD+N of the amplifier at 1 kilohertz and 6 kilohertz. This is the conventional way of people quantifying the performance of the Class D audio amplifiers. And then if you look at the peak THD, that's total harmonic distortion, then we are also at the very state-of-the-art numbers. And this is another plot that you will often see when you look at the data sheet or paper of a Class D audio amplifiers or any audio amplifiers. What we do is basically we sweep the total harmonic distortion plus noise over the entire power range of this amplifier. So what you see over here is that at lower output power, the THD+N is higher. This is because it has a lot of noise, because in this case, the signal is very small, so mostly you see a lot of noise. But then as the signal goes higher, you have more output power, then gradually the noise becomes less of an issue and the distortion of the amplifier starts to kick in. So at a certain point, it will reach its peak performance. And then after that, because the signal becomes so big, now something will start to enter a nonlinear region. It's going to clip a little bit. So eventually the THD will drop significantly when it approaches a really very, very large signals. So if we look at this graph, we can again say that we have achieved quite a state-of-the-art THD+N with this work. And you can also see that our output power is quite big, it's quite wide when we can obtain a very nice THD+N. And then if I compare this design with the two-level quantizer, that is when you just use a normal one-bit delta sigma modulator, and if we again compare the different performances, you can see that with the normal one-bit delta sigma modulator, the performance is much worse. Now, this is again because with one-bit delta sigma modulator, you have a lot of quantization noise, so the loop has to process all that noise. So it means that as the signal goes higher and higher, plus those noise, the loop will have a lot of more burden when the signal is getting bigger. So the signal, the loop at a certain point will reach its maximum capability much earlier compared to the multi-level quantizer design. So that's why you see the performance degrades quite a lot at an earlier power level. And then I think this one is about the EMI measurement of this work. So over here again, you see that without any multi-level quantization, when we have just a two-level mode, then we're barely meeting the EMI mask over here. But then when we are using the 17 level, then we have a really nice margin. Now, things will get even more obvious when we introduce some mismatch in the LC filters. Now, remember, all these LC filters, they are external components. So when you're selecting these components, they have a mismatch, and it's really difficult to quantify and to make sure that every LC filter you use matches nicely. So you always have to assume a certain mismatch. Now, when you have a mismatch in a fully differential system, now this will introduce differential to common mode leakage, and that will deteriorate the EMI performance. So in this case, when we introduce a certain mismatch with the 2-bit design, you see that it does not meet the EMI mask at all. But with the 17 level design, we are still meeting nicely the EMI mask. And then something about efficiency. So this is something I talked about at the very beginning. This is why we use Class D amplifier, because if you look at the efficiency for a really wide power range, you're getting about 90% of the power efficiency, which is much better than the other amplifier classes. And then this is a really big table, but if I can highlight, in terms of THD+N, which is probably one of the most important parameter in audio amplifiers, this work has achieved a really good performance. And then a major motivation of going to high switching frequency is to reduce the LC cutoff frequency and therefore to reduce the size of this LC filter. Now over here, you see that compared to some of the relatively conventional designs, we have achieved the best or the highest LC cutoff frequency. So these are the two highlights of this work. And then our next step is what to improve. We want even smaller LC filters. That is always a driver for the industry to reduce the cost and bulk of the system. And the second thing is that we also want to have a lower idle power consumption. What does that mean? Well, the idle power consumption means that The Class D amplifier is a switching amplifier, so it's always switching. Now that is happening even when you have no zero, even when you have zero audio signal. So that doesn't sound very economic because, okay, it means that when your amplifier is not playing music, it is still consuming power. That's not good. Well, some of you may ask, okay, why don't you just turn off the Class D amplifier? Well, it turns out that this is rather sophisticated because when you're turning it off and turning it on, it can produce some pop, and then you can hear this in your speaker. And so most of us don't want to hear that. So it turns out that people just keep it on all the time, even when you're not playing music. So we want to reduce this switching power, that is what we call idle power consumption here. And that means, and of course, this power consumption has something to do with the switching frequency. If you switch it faster, then there is more idle power. If you switch it lower, that is less idle power. So having a higher switching frequency definitely means that we are more prone to more idle power consumption. So how do we actually improve this? So then we have two approaches to solve this. First of all, for the LC filter, we want to employ even higher switching frequency for a very simple reason. But then how about idle power, right? For this one, we are proposing a 3-level output stage switching scheme, and that can actually lead to less switching activities, and therefore less EMI and smaller LC filter. So this is what I'm going to talk about in the next slides. So again, over here, you see that on the left-hand side, we have the conventional PWM modulation where you have a carrier and then you have an input signal. So you compare the two and then you get the PWM output waveform. Now that is clear. And now if you increase the frequency of this carrier, you can imagine that you will have a more dense PWM waveform, therefore more switching activities and thus more idle power. Now, how can we actually reduce that? Well, this is what the modulation scheme that we are proposing on the right-hand side. So over here, you still have this analog signal, that's the green curve. And then we introduce two carrier signals that is the complementary of each other. Now, how does this work? Well, when the signal is above, let's say the two carrier signals, it will introduce a pulse that is high. Now, when the signal is above one of the carrier, but is below the other carrier, then we output a mid-rail signal. And then when the signal is below both of the carrier signals, then we output a low-level signals. Now, you can imagine if the signal actually stays in the middle point of these two carriers, then the pulses that is going to produce is theoretically zero. So that means if I have a signal that is perfectly aligned at the middle point of these two carriers, then the output stage is not switching. So in this way, we can realize, we can minimize the switching activities in the Class D audio amplifier output stage, and therefore we can reduce the idle power consumption. So this is the modulation scheme we are proposing. And at the same time, you see that instead of switching between the full supply rails, like the one that is on the left-hand side, we are now switching only half of the supply rails. So this also means that we are reducing the switching energy, and therefore this is also good for the EMI. So by making this modulation scheme, we are able to increase the switching frequency, but still have a good chance to reduce the idle power consumption and also to relax the LC filter component size. And now some of you may say, okay, you talked about having very narrow pulses is not so good for the output stage because they cannot catch up. How do we actually cope with that? Well, the nice thing is that when you can increase the switching frequency, you can again increase the loop gain. Increasing the loop gain will help to compensate the effect of these narrow pulses. So then the next question is, how do we actually implement these three different levels? right? So normally a Class D amplifier has only the ground and the supply. So now we're introducing a mid-level. How are we going to do that? Are we going to use another supply that will employ a DC-DC converter and so on? Well, that would not be economic. So, and indeed, this is what some of the publications have done in the past. They introduce a different supply in this system, but this is not economic. And another way to introduce extra level is to use this kind of a multi-level output stage where they use a flying capacitor. Now you can imagine that this flying capacitor is basically like a tiny battery, and they can charge it to half of the supply. And therefore, this flying capacitor can introduce the third mid-level. Now, this one is rather complicated because you want to make sure that the charge that you dump on this capacitor is always sufficient. And sometimes it's not, sometimes it's a little bit over. So you always have to do some monitoring of the charge on this capacitor. And that makes this approach a little bit difficult. And then there is another approach that looks much simpler. And that is basically you introduce this common mode switch. And what you do is that you open all of these 4 switches, and then you just close these 2 middle switch. And if everything is balanced out, then these 2 points will stay at half of the supply. But of course, you can imagine, because all of these 4 switches are open, so these 2 are at a very high impedance node. So a little bit disturbance at these 2 nodes would actually make these 2 nodes voltage to fluctuate, and therefore you may not end up right in the middle of the supply rail. So how are we going to solve this problem? In this work, we are using an external capacitor, that is a common mode capacitor, and then we are introducing 4 common mode transistor switches. So what happens is that when we need to output the mid rail, we're opening all of these 4 switches, and then we're closing these 4 switches, and therefore the output common mode level is fixed by this external capacitor. And this capacitor only needs to be charged at the startup of the whole operation by a very simple on-chip voltage regulator. So how does this stage work in detail? Well, over here is that I'm showing the different scenarios of the output stage. One scenario is that we are turning on the red transistors so that the current is being drawn from the PVDD, and then it goes to the speaker, and then it's dumped to the ground. And then what happens is that we are going to switch state. And during this switching state, we have a dead time where all of these 4 switches are off. Now, you know that inductor current must always continue. So the inductor current must always have a current path. And how do we make sure that this current will flow? What we do is that we turn on these red switches over here, and then the current will flow, find its path, because the other switches, they have the body diode. So these body diode would again create a current path. And so what happens is the differential current actually just circulate in this loop. And none of these differential current actually needs to be supplied by this common mode capacitor. So that is the beauty of this topology, meaning that if everything works nicely, this capacitor would just stay there. You don't have to charge it. You don't have to think about the voltage on top of it. You only need a very weak voltage regulator to make sure, okay, it doesn't drift too much. And then vice versa, when you are switching in the other direction, you're drawing current from the PVDD, and then it's going through the speaker and then dumping to the ground. And then when you are switching state, there is a dead time. All the 4 switches are off. And in this case, we're turning on these 2 transistors, and the inductor current will find its path again in this loop through the body diodes of these the extra transistors in this common mode loop. So again, in this case, the differential signal is circulating, and there is nothing really needed to be provided from this common mode capacitor. So the nice thing about this approach is that you don't have to worry about charge balancing. You don't have to worry about the high impedance node that being disturbed by anything from the environment. So all the differential current is basically circulating in the loop, and this common mode capacitor can be basically standing there and only needs a very simple voltage regulator to maintain its voltage. And then again, this loop has third order loop filter, and with this very high switching frequency, we're able to achieve a very high loop gain, 82 dB. And just to give you an idea, in the conventional Class D amplifiers, the loop gain is roughly at 20 dB, 30 dB-ish. So in our case, we're able to pump it really to the next level. And this also is very helpful for us to achieve very nice linearity and also to circumvent this narrow pulse effects. And then at the same time, we're using the feed-forward structures. And in this way, if you understand a little bit about the delta sigma modulator, then you know that this helps to reduce the output swing of these integrator amplifiers, and that also helps to improve the linearity. So in the end, we have also implemented this work in the same process. And at this time, very noticeably, the LC filter cutoff frequency has increased to 580 kilohertz. Now, if you still remember, the previous work we did has a cutoff frequency about 100 kilohertz. Now, we're able to increase it almost by a factor of 6 in this work. And then if you also remember with this special 3-level modulation scheme, we are able to achieve very, very low switching activities when the signal is 0. So in this graph, what you see is that this black curve is the signal, and which is trying to transition from a negative value to 0 and then to positive value. So you see that when at negative and positive, the output stage is switching as it should be, but around the 0 crossings, it does not switch that much. So this also resulted in a very low idle power, that is 7 milliamp. Now, it may not sound so low to some of you, but for a power amplifier that is outputting 10 watt, 15 watt, this is a very small idle power. And then at the same time, we have achieved a very nice THD+N, and this is thanks to the high loop gain that we have realized with this high switching frequency. And again, this is the THD+N plot with the output power that you typically see in audio amplifiers. Again, we have achieved a really good THD+N, even at a pretty high output power level. And again, about the efficiency, not surprisingly, the Class D amplifier is still pretty good. And then we also did a lot of EMI measurement. In this case, we have swept the EMI from 150 kilohertz to 30 megahertz with our amplifiers, and also with different kind of EMI regulation scheme. So that's peak radiated emission and average radiated emission. And then we also swept from 30 megahertz to 200 megahertz. And again, we are meeting all the requirements. You don't see any tones that is penetrating through the EMI mask. And also even up to 1000 megahertz, it's still the same story. So it means that with this Class D amplifier, we have really achieved very good EMI performance, even with this 580 kilohertz cutoff frequency. So again, if you compare this amplifier performance with the other state of the art, you could see that very noticeably, our cutoff frequency of the LC filter is much, much higher compared to the other state of the art. And then also you can see that our switching frequency, that is 4.2 megahertz, this is also the highest in literature so far. And again, because of the high switching frequency, we are able to achieve a very nice linearity performance. And at the same time, if you look at the idle power consumption, that is also not so bad, especially when you compare it with some of the other works. And this is also thanks to the special 3-level modulation scheme. So after that, we think about what do we have to improve? And it turns out that one of the things we want to really improve is the LC filter size. And we have been thinking about mostly how to increase the LC filter cutoff frequency to reduce the LC component value. However, we find out that if you...
Dr.
Yes,
Fan?
yes.
I was just wondering, do you know approximately how much longer the presentation might run?
I actually still have some content because, yeah, I put a lot of, let's say, quite some of the basic explanation there, but I can also probably quickly go through the rest, maybe 5 minutes.
Okay, that would be perfect. Okay.
Yeah, sorry about that.
No problem.
A little bit techy, I realize.
Okay, good. Thanks.
Yeah, but I'll go very fast in the last part. So the simple story is that we realized it's actually not most effective to reduce the LC filter cost and bulk just by reducing their component value. Actually, it is more effective if you can tolerate more nonlinear component. Now, this is what I'm trying to show over here. So if you look at these two inductors, the left one has a higher inductance value, but it is much smaller and it's also much cheaper. Why? Because it has a much worse linearity performance. So means that if your system can tolerate these kind of nonlinearity, then it's going to be a very low cost. So this makes me come to the feedback after LC architecture, which is also what I mentioned at the beginning. So when you have these LC filters, they introduce nonlinearity. And if you don't correct them, they would basically limit the system nonlinearity in the end. So what we want to do is we want to incorporate this in the feedback and to make sure it works. Now, there's quite a lot of complications in how to make this loop stable. But the basic idea over here is, again, when you have a higher switching frequency, you have a lot more freedom to play around with the zeros and poles in your loop. And therefore, you have a much better chance to stabilize the loop and to get rid of this phase lag introduced by this LC filter. So I think I may just skip all of these, maybe this one. So this is how we do it. We basically just very simple. We have implemented a lead compensator over here, which basically corrects the phase shift of the LC filter by 90 degrees. So then that can help to stabilize the entire loop. Now you might say that why is this so difficult to do in the conventional class D? Again, the story is that if your loop bandwidth is very small, then you don't have a lot of frequency wiggle room for these lead compensators to really take effect. So I think I can probably just go over all of these. And over here, this is basically what we have implemented in the end. We have implemented an NTF that is around the LC filter. And this one basically means how much suppression you can obtain without how much you can suppress the LC filter nonlinearity. So minus 90, 49 dB means that if your LC filter nonlinearity is minus 60 dB, then with this loop, then you can gain another 49 dB improvement in linearity. And then we also have another NTF. This is for the output stage. So this is a little bit better even. So that means with the output stage nonlinearity, you can get 82 dB improvement in there. And then I think I would just jump to the measurement results. So over here, you see that we have measured the Class E amplifier with different inductor sizes. And that is basically due to the different nonlinearity performance of these inductors. And over here, you see the results. So the solid lines, these are the nonlinearity of the system after the feedback after LC correction. And the dotted lines, these are the nonlinearity of these LC filters. So you can see after this correction, we have achieved a very nice linearity performance, almost regardless of what inductor that you're using. So again, these are some of the measurement results. I think I will just go very quick. So in the end, we have shown that with this feedback after LC structure, we have achieved 49 dB suppression in the linearity. And that is quite effective, and which allows us to use a smaller LC. So to just summarize the entire talk, I hope it's still interesting for the audience. Well, we've talked about Class D basics, and then the high switching frequency basically have two benefits. One is to increase the loop gain. That helps you to increase the linearity of the system. And another thing is it helps to relax the LC filter size. And this is not only just about LC filter color frequency, but it's also about the LC filter nonlinearity correction. And then I have talked about some of the work we have done in the lab. And then that's it. That's the end of my talk. Thank you.
Thank you. Excellent. Excellent presentation.
Yeah, I'm sorry. I think it's I was trying to make things a little bit more understandable if people are not from the background. So I hope it still could make sense. Some of the
actually,
audience.
I've received more compliments in text messages about this presentation than any that we've had so far this quarter. So I think it paid off to give a lot of background information and get people up to speed. So it's great. It's really a great presentation. So I will, I think we still have a fair number of people online. I think at our peak, we were probably around 90 or 100, and now we're down about 45. It seems to be dropping quickly though. Are there any questions from anybody out there? I have one that I received in the chat, which we can get to. From Malcolm. Are there any questions? Oh, Vishvesh, go ahead.
Yeah, hi, Qinwen. Thanks so much for a fantastic talk. It was extremely accessible. And as someone who's not a practitioner in this field, I thank you for it. Chris, should we just prioritize the student questions first? I can ask mine.
No, I think, well, okay, there is a question that came from earlier, Vishvesh, so let's maybe take this one quickly. Wondering if Dr. Fan could summarize why a higher sampling rate wasn't used before. Seems like in prior applications, why did people not use? I think I know the answer to that, but I'll leave that to you. Higher order loop filters and the quantization schemes were certainly doable before. Great talk and thank you.
Yeah, that's a very nice question, and I'm curious to hear your answer actually, Professor.
No, you're the expert. I don't want to. Well, am I being tested? Am I being tested? My answer, I guess I would have guessed that people weren't really doing these things in CMOS before, and therefore this is still relatively new, and so raising the sampling rate is to very high frequency is probably something new. I don't know. That's my answer.
Yeah, I think you got it mostly. Okay, well, yeah. All right. Right. I think it was several things. One of the stuff is the technology advancement. Let's say 10 years ago, when I was a PhD student, I was still using 0.7 micrometer technology. And then those transistors are much, let's say, difficult to drive compared to what we have nowadays. So when you're talking about the slew rate, let's say the transition rate of those transistors, then we're probably talking about very different numbers at that time. So at that time, people were probably reluctant to drive them at a higher frequency. One thing is simply because the transistors are difficult to drive, they're slow. So you can't do it with a very high frequency. And another thing is that when you're switching at a higher frequency, you have more switching losses. And again, because those transistors are not so good, they're so, let's say, bulky and so much parasitic capacitance is associated. So you will have to consume quite a lot of switching power just to drive them at 2 megahertz or even 4 megahertz.
I see. Yeah.
Nowadays,
Good.
with the technology advancement, it looks like it's quite doable, and it's really not that bad.
Yeah. Yeah.
So I think you just have to do it. Yeah.
Exactly.
Yeah.
All right, Vishvesh, you want to fire one off?
Yeah, Qinwen, could we move to slide 25? I just have a couple of just minor questions, and then
Yes.
maybe a broader one, which we can take offline, depending on the length of the answer. Slide 25.
Yeah, 25.
Yep. So I think you were explaining around this point what the complexity was with really narrow pulse widths, because the transition times are so large. And I guess sort of the naive solution would have been to just have a steeper triangle wave and suppress the DC level of that PWM so that you have a minimum pulse width in your PWM solution. Am I missing something there? I imagine someone must have immediately tried that, but there's probably a good reason why that's a bad idea.
Yeah, the thing is that with the supply rails, it is usually determined, let's say in the automotive, right? Your supply rail is just, let's say 14.4 volt or something like that. So you actually don't have the freedom to squeeze your supply rails and manipulate the PWM pulse. So I think what you're suggesting is that, okay, instead of having a very large supply rail and a narrow pulse, how about I have a smaller supply rail and a wider PWM pulse? So that if you look at the PWM, right, what really matters is the area of that pulse. So in fact, you could say, okay, they're equivalent, but in the reality is that the supply rail may be just detected already by the system.
Oh, no, I guess if we could move maybe one slide back, I'll just quickly follow up on that. This triangle waveform, for example, if I were to bring it lower, if I were to bias it lower and compensate by making it steeper, I would end up with a scenario where I have a guaranteed wider minimum pulse width without changing the supply. That seemed to be like a very naive, intuitive thing to do first off. But I was wondering why maybe that wasn't tried or whether there's a reason for not doing so.
Yeah, so first of all, when you're manipulating the triangle wave amplitude, you're actually also manipulating the dynamic of the loop. I didn't talk about that again. I'm sorry about that. So with the PWM modulation, you actually have a, let's say a PWM factor, which is just a ratio between the supply voltage and the PWM carrier amplitude. And you can model that into your system. When you're changing that, you're basically changing the loop dynamics. So if you're reducing the carrier amplitude, you are pumping up the PWM modulator gain. And to maintain the same, let's say, loop bandwidth, then you have to push the loop filter to a lower frequency, for instance. So these are the things that you have to consider when you're doing this. And of course, if you push it so low, then noise and all that kind of stuff will start to kick in, right? You probably want to have a very, very small triangular carrier. And even in that case, you will still theoretically have very narrow pulse, because with PWM, the thing is that when you go for full scale, your signal will be touching the tips of those triangle carriers, no matter how small you make them or so. So theoretically, you can always approach infinitely small pulses.
Yeah, that makes sense. Yeah, thank you so much. On slide 31, this was a really, this was something I was really hoping you could help me understand as well. This one, when you went double-sided, what confused me was that it seemed like now you were effectively cutting back your frequency in terms of the harmonic content. And I was wondering if you could just help me navigate that.
Yeah, so the motivation of going to a double-sided in this case is to reduce the switching losses.
Yep.
Because literally, if you look at the frequency spectrum, it basically gives you the same quantization noise. So instead of having, let's say, twice of the switching losses in this one, it would better to go with this one.
But doesn't the PWM harmonic content move in back?
Yes, that's a very good question. So what happens is basically we are choosing a 4 megahertz sampling frequency.
Got it.
Going to double-sided sampling, you're basically moving the tone from 4 megahertz to 2 megahertz.
Okay.
Now, why is that not a problem? That is because for the CISPR25 class E for automotive, you see that there is a huge gap actually between 2 megahertz all the way up to 6 megahertz. So you can afford to place your PWM tone just a little bit above that EMI mask.
I see.
So instead of putting it at 4 megahertz, yeah, you could just put it at 2 megahertz and save half of the switching losses.
Okay.
And
that's really nice.
Yeah.
Okay.
Right.
Okay. Thank you.
That's a very nice question.
Okay, good. I see Ahmed is still online. He had a question that he put in the chat. Ahmed, do you want to quickly ask your question? You'll need to unmute. Okay, I guess I'll ask it in the chat. He said, the question is, I was thinking that since most of the audio signal power is low, I suppose in frequency, or maybe power, actually, I'm not sure, maybe power. As you mentioned in the non-uniform quantization part, can we use PFM instead of PWM to relax the output stage switching?
The PFM?
Yeah, PFM. Ahmed, I see you're online.
Yeah, I'm sorry. Yeah,
Yeah.
I was just AFK for a couple of seconds. Yeah. So basically, yeah, that's it. Yeah. So like, so first of all, thank you very much. But I was wondering if you can like do some like pulse frequency modulation instead of pulse width in order to relax the low frequency components in terms of frequency. Yeah.
Yeah, again, that's a very good question. So I didn't talk so much about pulse frequency modulation. There are actually quite some audio amplifiers in that. We're sometimes calling them self-oscillating Class D audio amplifiers. And the thing with this type of amplifiers is that the switching frequency changes with the audio content. And what you ideally want to do is, okay, when you have no signal, you also want to have a relatively slow switching frequency, which is very nice for the idle power. The only tricky part is that if you use this for automotive application, you want to make sure that you're not switching in any of these bands. Let's say when you're changing your signal content, right, the spectrum of those self-switching audio amplifier usually doesn't look like this. It doesn't have tones, but it all looks a little bit more smeared. But
with this given bandwidth.
Right, but the noise is still going to have a relatively like a peak somewhere, and you don't want that peak to fall into these EMI mask range. So that is why you sort of want to keep it contained. It is better to have something that is very sharp, but you know for sure is going to be above the mask, than to have something, you know, maybe it will meet the mask, but maybe not. So that was the main concern, let's say, why we didn't go for modulation for this particular application. However, in other applications where you don't have these strict requirements, that could be a very nice approach, actually.
Thanks again. Thank you very much, actually.
Yeah. Okay. Actually, I just have one question. I think it's probably a simple one. Like if you go to slide 18, in that diagram that you have, so you show the LC filter, and then you show a cable that's going out to the speaker.
Yeah.
And I'm sort of wondering, is that speaker? I assume that wire is negligible, right? Because I'm assuming you mount this driver right on the speaker itself. Is that correct?
That really depends on the application. In cell phone, for instance, that's often the case because everything is so close.
Yep.
In the car, we learned that is often not the case. And this is not up to us, the electrical engineers, to do so. It's really up to the car manufacturers.
Yep.
And sometimes they just don't care about this. And
what kind of lengths are we talking about? I'm a little curious. In like automotive, what's the worst case? I guess is what I was trying to get at.
I'm afraid I also don't have that number. But
well, I guess the thing I was thinking when you presented this slide, one thing that came to mind is I was a little bit curious. I mean, it seems like from the perspective of the audio amplifier, right? And
Yeah.
reducing distortion. The ultimate would be if you could, let's say the cable was long. Let's make an assumption it's an automotive application and the cable
Right.
is, I don't know, a meter and a half long. And you know, would it be advantageous somehow if you could grab the signal right at the input of the cable? I mean, right at the input of the speaker, and wrap that back around to the input of your delta sigma.
You could do that, but I think the damage is still there because the EMI the EMI content is still there as long as you use a Class D audio amplifier, right? So all of these high frequency content is still there, and they get emitted through to the other circuits.
Right. Okay, sure.
Yes.
That in that direction, but I was thinking the other directions. Actually, that's what I was sort of curious about. What about EMI that's coming from other sources that couples onto that line? Is that a concern? And if the answer is yes, would you benefit from somehow being able to sample right at the input of the speaker on the other side of the cable?
That's a very interesting question, and I also don't know the answer. So first of all,
where I was going with all this is, so the cable seems sort of, a longer cable I think would be problematic. I mean, not problematic, but I mean, there is a potential there to pick stuff up, but of course these things are wrapped in coax and things like that. But what I was sitting here thinking as you were speaking is, you know, I'm kind of wondering if you could take a radio, like, you know, some very low power radio, and hook it to the output of your sigma your driver basically, and then connect it to the speaker, and then you could have sort of a two-way, you know, communication over that radio, and then feed it back to the input of the loop filter. That's kind of a crazy idea. I think about radios sometimes, so that was one thought that came to mind. So then I was just kind of curious how long this thing can be. Okay, so you have written 10 centimeters, you know, that's, you know, it's not long, but not a stub. So yeah, interesting.
Yeah.
All right. This is great. Okay, so I think, man, this has been a very successful talk. Everybody stayed on to the end. Usually the students drop out really fast, right in the middle of, you know, like by like 12, we start losing a lot of people. So I think that's a sign that this was just a really interesting talk, and people really appreciated it. So I would like to thank you. And if there's still people on the line, I suppose you could send Dr. Fan some email if you have further questions. But I think that'll conclude our colloquium. So again, thank you very much.
Thank you very much for having me here.